All right, we're getting a little late start, but then again, we have half the class missing, so.
Eli.
Wait.
I think he's Eli Lilly.
Oh, Orfeld.
Yeah.
The Orfeld show.
Oh, but he did, that was just Chris. I didn't think Clayton made it too nice.
Oh, it didn't?
Yeah, what's,
Oh, then maybe it is a little.
It's
He-
Eli Lilly.
what's Blake doing?
All right,
Oh, he's just getting big.
today we're talking about polymers. Things like, you know, silica.
So,
Oh.
really?
Ugh.
Oh, this one's really good.
Yeah. The rest of
Well, if you read this one, it will no longer be good because the stuff will run out, but just great. Practice responsibility.
You practice shooting things into that trash can? Because I'm pretty sure I've never seen you miss. You're like,
He
oh,
missed
man.
in a status
Like
last year
lunch.
at one point.
Lunch things, old markers.
No, it didn't.
he just sits in his room.
It's like your break during the day, like coming
That's
here.
what I do, that's how I
Drop
spend my
buckets.
time. That's right, exactly.
He comes back.
Always
with
one.
I don't actually, I wing it when I'm teaching, because all the rest of my time is practice throwing the garbage.
That's-
All right, polymers, there's two types of polymerization. Two ways to form polymers. The first is chain growth, called addition polymerization. The advantages of chain growth is that it's a rapid process. Whether it's an advantage or disadvantage, it usually produces linear chains. And the MERs that are most useful are the MERs that can be most effectively used for this are bifunctional MERs. That is MERs with 2 points of contact. So for instance, we have polyethylene. Is polyethylene what I did on the?
Yes.
Was that on a test or on homework?
It is.
It sounds familiar.
So we have N C2H4 molecules, N ethylene molecules. And through polymerization, they become C2H4 sub N. So that's how you write it. This is the degree of polymerization.
That's nice.
So if I have a degree of polymerization of 10,000, that means I have 10,000 MERs. Okay? So usually there's some kind of an initiator. Or terminator. So this is what ethylene normally looks like. Or, yeah. So each of those. And what happens is I bring in an initiator, an OH minus. And there's a stronger affinity for this carbon bond to flip over here onto the OH minus. So I end up with OH, technically it would be HO in this configuration, but the OH out here bonded with the carbon, bonded to the other carbon, and then a free radical out on that end. So that then another can come in and join it, break that bond, form it here, leave a free radical. And you can see it's a linear process. Yes?
Does it not indicate a free radical?
Yeah. Yes.
Why is the initiator necessary?
Why is the initiator? Because you need to close off the end. Because in other words, if I just form this to, this to another thing, I would end up with a free radical on both ends.
So does it end with
What's that?
Does it end with it closing something?
Right, because it's not, that's not stable. Having a free, the free radical on the end is not stable. So, oh man. So, since it's not stable, it will want to close itself off. And since in aqueous environments, there's plenty of OH floating around. There's always something to close it off. But it could also be, there are other groups you put out here. What's alcohol? You took organic chemistry. What's alcohol?
OH groups on the compound.
Okay, so this is alcohol. So this is,
That's an alcohol.
okay. But there are other. Anyway, there are other groups. And then it just continues. As we continue to add more groups until we finally terminate with another OH. All right. So there's some variations on that basic theme. There's the copolymer. So for instance, if I took MERS of ethylene and I don't know what that's called. And replace one of the hydrogens with chlorines. Then I could end up with a copolymer, which was something like this. Right? So I've got a bunch of different MERS. Some of them are of one species, others are of another species. So two different MERS. Or I could have three different MERS. Some of them could have, I could do the same thing. Some of the places I have two chlorines in the base MER. The point is you have two or more different MERS interspersed along the chain. So that's a copolymer. It's kind of like a solid solution in alloys. Where they're easily interchanged between each other. The MERS are easily interchangeable. So within copolymers, we can also have block copolymers. Where you just have contiguous chunks of one type or the other. So here we basically grouped like MERS, I guess. So you have all the chlorine chunks down here and then all the non-chlorine chunks and so on. The block copolymer. Then there is the blend copolymer. Which is just a physical mixture. Rather than a chemical mixture. So I could have a big chain of chlorinated polymer and another chain of non-chlorinated polymer, and they're just physically mixed together. They're not chemically bonded together.
So like, kind of like if you did like one kind of rope where they kind of just like swarm around each other kind of thing?
It's like mixing fettuccine and spaghetti together, right? So it's basically just a mixture of the two, they don't bond. And then the last copolymer is a graft copolymer. or actually grafting something onto the side. So a graphical polymer then, I'll come back to my picture here. So I just take poly off the name. A graphical polymer could be me doing this. Right, maybe, and maybe these are all chlorinated, maybe they're not. Okay, but I grafted onto the side. Okay, so then kind of, you have a host chain and then things branch off from the side.
Would that happen just like one or two of them, or just like a bunch of them? Or it can just be any of them, depends.
It would be, if it happens once, it probably happens again.
Okay.
It's based on how you conduct the reaction to form the polymer in the first place. And the affinity of the material for having a side branch on the side. Okay. So that's all the addition polymerization. Chain growth. Any questions? Okay, the second type then is step growth, which is called condensation polarization. Here the reactions are 2 mers at a time. Instead of having a bunch of mers going brrr, you just have 2 mers, they come together, they bond. As a result, it's going to be slower. Right? You should do it one piece at a time instead of being able to sort of unravel the whole thing. We typically have polyfunctional mers. That is, mers that have more than 2 bonding points. You don't just bond on one end and the other, but you could bond in multiple places. Because these are polyfunctional mers, you can often form 2D or 3D networks. So it's not just a one-dimensional chain, but it's a 2-dimensional and 3-dimensional network of polymers. So the example your book uses is phenylformaldehyde. So you have a phenyl group. And another phenyl group. Formaldehyde comes in here. It's formaldehyde. And you can see here, right, I've got an oxygen and 2 hydrogens. Right? The water loves being water. And so I break this chain, I'm going to break this off. That water goes off all by itself, and I'm left with the carbon bonding like this. I'm pretty sure that this is where it gets its name, condensation polymerization, because it gets off, because many of them get off water. Okay. Now in reality, what will actually happen is it typically rearranges itself so that one of the hydrogens is up and one of the hydrogens is down. So it forms the tetrahedral structure around this carbon. We talked about that before, right? Like the carbon likes to form a tetrahedral structure. 109.5 degree angle, bond angle or whatever. So it'll actually form, these will be two legs of the tetrahedron. But the point is, then there's other bonding sites on the formaldehyde, or on the phenyl group. So I can actually form, in this case, you could clearly see a two-dimensional structure, but these things are actually three-dimensional, so you could potentially form a three-dimensional polymer.
Only two at a time, that doesn't mean polymer is limited to 2 MERS, right?
What's that?
You said step growth is 2 MERS at a time?
Right, so essentially these two MERS, you can think of this as being sort of a catalyst or something, you know, the bonding agent. But, you know, these would be your MERS. And then I could have another MER come in, another catalyst come in here, and I could form another thing down here between those same two MERS. Or, alternatively, I could have another, and I didn't give myself much room, I could have another phenyl group come down here, right, or could form a phenyl group could form in here in 3 dimensions, right, come out here and bond with those two. So you create more complex structures.
But it's still being strung together, sort of like.
But it's not being strung together end to end, right? It's not just this continuous part. It's not this, and then I form another phenyl, you know, another thing over here, and then I form another thing over here, right? It's not doing that. So it's not forming it end to end. It's forming these two form, and then these two form, and then those two form, and so on. And so you can get much more complex structures. Okay. Okay.
Is the dash without anything attached to it, is that understood to be hydrogen, or, yeah, hydrogen next to it?
Was anything an empty bond?
Yeah.
Yeah. The empty bond means hydrogen.
And then can a single connector MER, can that form in step growth? Or, I mean, would it just technically be chain because it's just in the end?
Because they're bifunctional, so you're
Okay.
just forming.
So bifunctional isn't only chain growth, because it just is chain growth.
Bifunctional, really, a bifunctional MER will almost always form in a chain group mechanism, because the only time it would not is if it, I suppose, if it were, if there was some other mitigating factor that forced it to, you know, to form 3-dimensionally. But generally speaking, bifunctional MERS, you know, one activity point here, one activity point here, you're going to form a line in that direction. All right. And I talked about this a little bit earlier in the semester. We visited here about crystallinity in polymers. Remember we talked about crystallinity in polymers? So, in general, the only polymers that actually form crystals are the linear chains, because they can do this. They wrap back and forth on themselves. Shouldn't have drawn this so big. And then you get the same thing going in the back here. Right, and then again. Okay, you get the general idea how it wraps up itself. It can occur with other, you know, non-linear structures, but the majority of the time it's going to be something like this. But again, that's something we've already talked about before, so. Okay, so we've already talked about that. Structure. Crystalline. Next thing in structure is polymer length. So clearly, I can figure out the length of a polymer by adding up the length of each one. Right? So if I have the polyethylene that I showed you before, and we know that those carbon-carbon bonds are at 109-degree bond angle, right? I can calculate called the extended length. Which is equal to m times L sub x, where L sub x is the x component of the bond, of the single bond, and m is the number of bonds. The most common one is the carbon, excuse me, where this is 109.5, so that L sub x is equal to L, the length of the bond, times the sine of theta over 2. Sine, right?
Is that 104 or 109?
109.5. I think that's the right? So that's the extended length. If I take that polymer and pull it all out into a full long chain, that's as long as I can get that chain. But that is not typically the way the polymers exist. Right? If I have a chunk of polymer, it's not typically all the chains lined up in a nice straight line. So what's more likely, what we're more likely to refer, or we use to characterize the length, is the RMS length. Because this chain, if I now kind of zoom out a little bit, right, it can be, right, this big long thing, right? So the RMS length is the length from end to end when it's sort of randomly oriented like that. And without going through a great deal of derivation, L bar is equal to L times the square root of L. L being the length of a single bond, M being the number of bonds present. So those are the two ways we can characterize the length of the bond. Okay, what else do we have? Oh. Strengthening mechanisms. As I talked about before, polymers are not terribly strong. Right? When we talk about mechanical properties, I talked about the fact that you pull on a piece of polymer, and the first thing you're going to do is just overcome the van der Waals forces that are holding multiple chains together. I'm going to take this chain and straighten it. And the only thing opposing me taking that chain and straightening it is the van der Waals forces that are holding the different pieces of the chain together. So polymers are typically fairly small, fairly soft. Right? Overcoming van der Waals force is not that strong, or not that hard. So we need some strengthening mechanisms to make them stronger than just the van der Waals forces. So I got three different strengthening mechanisms. One is to add side groups. So if I have my chain, a big long chain here, and I just add up here a carbon group, right? And then down here someplace I add another carbon group. Couldn't decide if I wanted to try to do it tetrahedrally in 3 dimensions or just go on 2. All right, so I've got this chain that keeps going on down, and they have these occasional side groups. Well, that's going to make it a little bit easier, because if I have a side group, if I have one chain like this, and I have another chain that's along here, and it has a side group coming off here, right? And I try to pull them past one another, they're going to hang up on each other, right? They're going to snag. So adding side groups, even if they're relatively small, can strengthen the polymer, because it creates a mechanical interference to deformation, yes.
Jumping back to the RMS length real quick, I'm confused what L is there, is it just like?
L is the length of a single bond.
Oh, wait, okay, so it's still a length.
Same L as the same L that we
Okay.
had over there. Okay. All right, we go with the side groups. Even more than the side groups, branching. Branching occurs when the chain does that. I'm adding groups, adding groups, adding groups, adding groups. And then instead of breaking this carbon, instead of the carbon replacing that hydrogen on that side, it now goes up. Right, so instead of now, the next C is up here. Right, so I have two hydrogens there.
So, but with that case, literally the only thing that's holding that L shape is the one carbon, you know, degree thing. So what's to keep it from just easily just kinking
Well,
it?
typically what'll happen in that case then is I'll actually continue to form down here. So this branch will become.
Right, so then how's that different from side groups?
A side group doesn't have to be the same core thing.
Uh,
Right, this could be some kind of an ammonia thing, right? Right, could be some kind of whatever, nitrogen group. These, the branching, it's typically the same thing growing off from the side. So it's not a graphical polymer, right? This is not a second kind of polymer, it's just a branch off of the main chain. That make sense? Okay, so basically, the branching is just long side groups. And so obviously, much stronger interference. And then the last thing is cross-linking. So cross-linking and two chains next to each other. And instead of the hydrogen in between, I put some other kind of a material that actually chemically bonds the two chains together. So I put a sulfur in there. Now I've cross-linked the two chains. So here we're using primary bonds. The weak polymer by itself has only secondary bonds between them. The side groups and branching, we're basically relying on mechanical resistance, not actually forming a bond, but here we actually form primary bonds between the chains. And I particularly chose sulfur, because sulfur is actually what's used in vulcanized rubber. Vulcanized rubber is taking isoprene. Hold on a second, let me see if I can identify. Isoprene would be, like that. That's isoprene. Nope, one more. Isoprene. So I repeat that structure along the length of the backbone here. And then this one might have C's here. And I can form an S in there. So I take isoprene, add some sulfur, and vulcanize it. It becomes vulcanized rubber, the stuff your tires are made out of.
That's just stronger than.
Because now, yeah, it's stronger, because they have a cross-link, right? So now it's at least a two-dimensional, or in reality, a three-dimensional system. I cross-link all the polymers together, so they're no longer just held together with van der Waals forces, they're held together with primary bonds. In fact, a bowling ball is an example. The way they make bowling balls is polyurethane. but they cross-link polyurethane. So that in theory, your entire bowling ball could be one molecule. We have all these little chains, but if they're sufficiently cross-linked, it's all one molecule. Okay? Now, I'm not sure that that's the actual ability to completely form one molecule. You know, there's going to be bits and pieces that don't connect, but the point is, you cross-link, you can actually make it one big strong thing. Primarily bond, you know, so it's primary bonded throughout the whole thing. Yep.
What is the actual mechanism to get those bonds so it actually work to form?
How's vulcanization happen?
Yeah, is it like you
So
add a chemical to it? That
Right, you have to do chemical at the right temperature and the right conditions. Right?
It's not like a mechanical.
So, all these are like super, super like specific things. I feel like a lot of these are carbon and hydrogen
That's
based,
what most
and then it's
polymers
just
are.
kind of like, it's carbon hydrogen this way, or maybe it's this way, maybe it's usually like just get the right, everything else around it basically.
Right, I mean, that's really what polyethylene, what's next, butylene? You know, there's not really any difference between those, they're just big on carbon change. Butyl's 4, right?
Butyl's 4, ethyl's 2.
That's 3.
Bro.
Polypropylene? But polypropylene, actually, I think, actual polypropylene is, maybe it's not, I'm not sure. I don't think it's necessarily a long chain. Anyway, so, okay, so strengthening. So that's how you strengthen stuff. Any other questions on thermal properties? There are two types of polymers, thermally, two types of ways in which polymers react to temperature. There are, what did I do first? Thermoplastic and thermoset. And basically it's all defined by what happens to them when you raise their temperature. The thermoplastic soften at elevated temperature. So you take a Coke bottle, right? You start to heat it up, what happens to it? Right? It can deforms, right? It falls under its own weight. It gets softer. These are typically made of linear molecules. So what's happening is the higher temperature, the temperature itself overcomes the van der Waals forces. So now the polymer can, because at the elevated temperature, the polymer chains can just slide relative to one another, just under their own weight. Okay. So temperature overcomes secondary bonds. It's kind of like high temperature creep in metals. Remember we talked about creep? Get high enough temperature, then the atomic mobility, we overcome some of the bond strength. The difference is that for creep in metals, it's something on the order of, like 1,000 degrees C. Temperature at which we overcome the secondary bonds is more on the order of 100 degrees C. happens, thermoplastic deformation occurs at a much lower temperature. Yeah.
Was creep where we kind of had the stress fell over time where it kind of like went up and then it
So the strain is
and then-
relieved. So creep was the fact that the you know, you take a piece of wire, hang a weight on it, and it should just sit there. But over time, it elongates because there's enough thermal energy to propagate the dislocations to remove the strain that's in the material.
So then we had like there was like a secondary bond section of it, and then we got the very end of the primary bond.
That was when we were talking about polymers. There's no secondary bond in metallic bonding. Okay. So, but the behavior is similar to what we can see in metallic creep, where it just kind of it can goo, you know, it can deform. But it rehardens at lower temperature. So if I cool it back down, it hardens up again. Right, because I cool it back down, the secondary bonds are no longer overcome by temperature, and so they reform. So I can heat it up, deform it, cool it off, and I'm back to ready to be. So this is the little Christmas tree ornaments I used to make with my grandma. Take little red plastic cups, stick them on a cookie sheet in the oven, heat it up, and they turn into this random blob of goo because it just sort of collapses on itself. And then you take it out and cool it off, and now it's hard. Actually, what you usually do is you punch a hole in it when it's soft, and then you hang it on the tree. Shrinky dinks. Everybody's done shrinky dinks. Right? Heat them up, they get soft, they kind of collapse on themselves because there's residual stress in them, and then you take them back out and they harden up again. All thermoplastic behavior. So examples of the thermoplastics. Polyethylene. PVC. We've done it with pipe. Your PVC pipe, you know, white pipe that you have in your house, whatever you get it, you get it keep hot, and it turns to, like if you cut it, the heat from the friction will get the stuff to deform, but then as soon as it cools off, it's back and hard and crispy again. Polystyrene. I can deal with a coffee cup. It gets too hot, it deforms, but then, all right. ABS, plexiglass, and nylon. All of those are thermoplastic materials, yes.
And when you're heating those up, what gases are they?
How are they outgassing? I don't know. I mean, hopefully you don't have to heat them so far that they, they outgassing more than they. But you're not actually inducing any kind of chemical reaction if you're doing this right.
Yeah, what happens, I mean, like at a certain point, they're just gonna start to burn, right?
Right, so at some point you put in enough temperature that you can actually break primary bonds.
Oh, that's what it
Right, but the idea here is to work at a temperature where you're not breaking primary bonds, you're only breaking secondary bonds. So we have go ahead.
What is the bad gas that comes out of burning any kind of plastic?
Well, it's mainly when it's chlorinated plastic. That's the bad gas. You mainly don't want to release chlorine gas into the atmosphere. But we have a plastic bender down in the machine shop. So it's basically nothing but a electrical, high resistance electrical bar, or electrical resistance bar. Anyway, a bar that gets hot when you pass current through. You just put a piece of sheet of plexiglass over the top of it, and the heat radiates off of the plexiglass, or off the bar onto the plexiglass. I mean, it's not so hot I can't touch it. I wouldn't leave my hand on it, but I could touch it, without burning myself. But it gets it hot enough that you can then bend the plastic. And then you just let it cool, and it hardens up again. Okay. So you can make acrylic, bend acrylic around the corners of your box. That's thermoplastic. Thermoset, thermosetting polymers are more typically network polymers. Right, so they're more likely the ones that grew by condensation polymerization. And what happens is you have incomplete polymerization. At room temperature. So you have this, you mix this stuff together, you mix the formaldehyde and the phenol, and you induce the reaction. But at room temperature, there's not the reaction isn't complete. There's bits of unbonded phenol and bits of formaldehyde left in the mix. So then, when I raise the temperature, it enhances the chemical reaction. So they raise the temperature, more of those formaldehyde groups bond to more of those phenol groups. So it's an even more complex structure. Right? There's more reactions, and now I have more bonds in different places in different directions. So as a result, it gets harder. So if this got soft at elevated temperature, a thermoset polymer gets harder at elevated temperatures. But since it's polymerization, it's actual primary bonds forming, it stays hard upon cooling.
So if you heat it up again, it would, nothing would happen because it's already fully.
Right, if you, yeah, I mean, fully, I don't know how
I mean,
fully it is, but yes.
So like, if you take it up to this temperature, pull it back down, take it back up to that temperature, it's not really going to change
Right, hard to
much of
do.
anything.
Right. As long as you leave it long enough to use temperature. So examples here are phenolic resins, like Bakelite.
Bakelite?
Bakelite.
I heard bacon like.
Epoxies. Rubbers. Both natural and things like neoprene. Silicone, which I guess anymore we still talk about silicone as a rubber. It's a silicone rubber. It's characterized as a silicone rubber because of its mechanical properties, not because of its actual structure. These are all thermosetting polymers.
So, it seems to me that I can't really picture having a polymer or plastic of some sort getting hotter and it gets harder. Like I could envision that for all the others, but maybe are they just more, are they a lot more
If
for
I-
plastic?
If you bake rubber, right, it loses its stretchiness. Right? Take a rubber band, get it hot in the sun, well, it embrittles, it melts.
So it becomes, well, it gets brittle, but it
Well,
also
you know, well,
melts.
yeah, that's what I'm saying, you have to get it in the right range of temperature, you don't want it to.
So if you get it too hot, it'll melt?
If you get it too hot, you get the, well, maybe too hot, it'll burn, but you know what happens to it. I mean, when you take a rubber band, get it hot and then cool it back down or whatever, it's less stretchy, it's
How
hard.
about rubber bands that just sit over time? Doesn't seem like anything happens to them if they get brittle.
It could, yeah, it could be a polymerization thing. It just gets, you just give it longer time. Right, longer time at room temperature is the same thing as shorter time at elevated temperature.
Does vulcanized rubber do that then? Or is it just like, it's a much hotter?
So vulcanized rubber could, yeah, vulcanized rubber could,
It
sure.
just takes it at hotter temperature generally.
Basically, you just don't have, you know, if you've not used all the sulfur from the vulcanization process, you raise it up to a higher temperature, you get increased vulcanization, makes the material harder.
Okay.
So some tires, you get, you know, very I don't know that they even use vulcanized rubber exclusively. Tires now are high tech, could be different polymers, but the point was you get softer or harder tires depending on how much you allowed that reaction to take place and how much sulfur you put in. Okay, I'm out of time. There's a section on additives. Read the section on additives in the book. Well, all right, never mind. I'll at least throw it up here. We got started a little late.
Is that still under polymers?
Yeah. Is there other additives you can do to change the properties of the polymer? Plasticizers. Plasticizers are added to soften the polymer. So you take PVC. If you don't put plasticizers in it, it's pipe. If you do put plasticizers in it, it's a raincoat. Still PVC, the whole thing's PVC. Okay. Fillers or reinforcements added to strengthening. That's why titanium, that's one of the reasons, titanium dioxide is in paint. It's a ceramic filler. Makes the paint harder. It's not just a rubber paint. Right? Latex paint, latex is a polymer. Put the titanium dioxide in there, serves two purposes actually. Both serves as a filler to make the paint harder, so make it more durable, but it also makes it more opaque. Titanium dioxide is white, is what you put in stuff to make it white. And it resists chain mobility. Basically, I have this hard piece of ceramic in there, the chains can't just slide right past it. Right. Third is stabilizers. Polymers are notoriously bad at UV degradation. Ultraviolet energy can break the bonds. And so you put stabilizers in there to reduce that degradation. Oxygen can break the bonds, right? These things are, well, they're gone now. You got all these carbons in there. They don't mind reacting with oxygen, right? Or pulling some hydrogen out with some oxygen, get some water, right? Oxidation can occur pretty readily. That's why the polymer, you know, the plastic shutters on your house fade with time. Between ultraviolet radiation and oxygen, you've changed the polymer, the properties of the polymer. Flame retardants, pretty self-explanatory, because the burning point, right, these things can burn. They're organic materials that can burn. So you put flame retardants in, things like chlorine, bromine, phosphorus, those sorts of things, to keep it from the hydrocarbons from burning. And the last thing then, also fairly self-explanatory, is colorants. You have a pigment, which is an insoluble ceramic kind of material, and is opaque, or you can have dyes. Pigments, or dyes. Dyes are, you know, so your 7-Up bottle, because it's green, because it has a dye in it. The dye is a soluble material, soluble in the polymer, and it's as a result it's transparent. The pigments are insoluble, typically ceramic powders, and they make the polymer not transparent, make it opaque. Okay, so make sure your folder purple, you know, this is purple, because it has pigments in it. But as I said, the 7-Up bottle is green because of dyes.
Those dyes don't become part of the polymer, though. They're just absorbed.
They are right. So they are dispersed within the polymer, but they're not. They're small enough that they don't interact with light, other than frequency absorption. So in other words, they don't. They're bigger. They're smaller than wavelength of light. So that their interaction with the light is just important. Certain wavelengths, it doesn't scatter. It's too small to scatter. So just individual molecules that get spread out throughout the mix.
So the powder stuff would do the same thing except for bigger.
So the powder, the pigment is typically not it's not transparent itself. Right? Or it's such a high index mismatch, index of refraction mismatch with the material that you're, the plastic that you're putting in. So titanium dioxide is transparent if I just had a solid chunk of titanium dioxide. But because it's powdered and has a very different index of refraction, it just scatters the light, makes it opaque, or it makes it translucent in small amounts, but then eventually opaque. All right. There you go.
As long as